Okay, this is a continuation of concentration and rate notes. We have finished this whole front and back of the first page. We just finished talking about units of the rate constant, and now we're over here using initial rates to determine rate loss. Okay, so I left you a good amount of space to tell you not a whole lot, so sorry about that. The biggest thing that I need to tell you here is that this is now about the discussion of how we determine the orders. Okay, so those orders, those exponents must be determined from data. And there's no other way. So this is where I said earlier, you're going to get very used to seeing charts like this. And our job is going to be, we have to figure out what's the order on A and what's the order on B so that we can start to complete this rate law. So, in the end, what we're looking for is to write some kind of rate law that looks like that, where we can fill in a little bit more information, particularly where we can fill in M and N. Now, I'm going to teach you two ways to do this. One way is by far easier and quicker. The only problem is sometimes students have a hard time seeing it, and also sometimes some problems don't lend themselves well to this method because the numbers aren't, shall we say, like nice numbers. It's kind of messy. So the first way I'm going to teach you to solve for M and N is the easiest way, and I call it just a visual inspection of the data. So some of you are going to like this, and some of you might not really understand it, and that's okay. There's going to be another way that's a more mathematical approach. So again, the goal here is to find M and N. Okay, so if you remember back from our first discussion of looking at a chart like this, if we want to know how A changes the rate, or if we want to know how changing A changes the rate, well then we have to look at two experiments where B is held constant, but A changes. So if you look through the table, the only two experiments that fit that are 1 and 3, because A has changed. Specifically, A has doubled from 1 to 3, but B did nothing. So any change in the rate is coming solely from A. So that's what we're going to look at for the order of M. So again, if you look right here, we doubled the concentration of A and the rate quadrupled. So doubling this, had this doubled, that would be a directly proportional relationship, and our exponent would be, or our order would be a 1. But that's not the case here. We doubled this, and this quadrupled. Well, that's the squaring of a double. So that means M is the order of 2. And again, you could kind of prove that to yourself if you were having some trouble. You could make up, a little bit simpler numbers than this and say, okay, well, if my, so let's say A is 1. We still don't know what M is. And let's say my rate's 1. We're just picking easy numbers. Well, so my rate quadrupled here when I doubled M, right? I doubled A and my rate quadrupled. So the only thing M can be there is a 2. And so now I have amended my rate law down here to reflect that. Okay, the other way, the other thing I have to take into account now is, of course, B and how changing B affects the rate. So now, if you want to look at how changing B affects the rate, you have to look at two experiments where A is kept constant. So the best two to look at would be 1 and 2, because in this case, in experiments 1 and 2, B is doubled, but A is held constant. And notice, even though I doubled B, what happened to the rate? Nothing. So changing B has no effect on the rate. And that was a very significant discussion earlier in one of the options for our orders. And that is that the only order it can be is a 0. Again, we can kind of prove that to ourselves over here with the same idea, saying 1 to the m, oops, it would be n this time, sorry, is 1, just for simplicity's sake. Well, then we doubled this, and this stayed the same. The only thing n can possibly be there is a 0. So here's my rate law. And actually, anything to the 0 power is 1. So this whole term right here, b to the 0, goes to 1. So really, my rate law for this is this right here. And that's the first approach to this method and to this example in this problem to determine the rate law. Now, like I said, so to some of you, that's not the best way to do it. I mean, you might not really like that method, and so I need to show you a second method, which is a much more mathematical approach, and it's a much more intensive approach, but we need to talk about it because sometimes you're going to be forced to use it, and some of you might just prefer it. Okay, so give me a second to get this cleaned off and started again. And unfortunately, I'm going to have to recopy this chart, so hold on one second. Okay. So here we go. Here's my problem. So if you hadn't figured out before, I might not have said, sorry, we're on this example 1. Okay, so the problem says the initial rate of a reaction A plus B yields C was measured for several different starting concentrations of A and B, and the results are as follows, presented here in this table. Using the data, determine 3 things. A, the rate law for this reaction. B, the magnitude of the rate constant. And C, the rate of the reaction when A is equal to that given concentration and B is equal to that given concentration. Okay, so based on what we just talked about, we have technically already calculated the rate law, but we did it in a method that, like I said, was just a visual inspection, and it might not be okay for most of you. So this is the way to solve for the orders using the mathematical approach. It's going to be a little bit work intensive, but you need to see how this is done. All right, so we're going to do the same thing where I'm going to focus on, well, here, let me jump over here. We know A and B are the reactants, so I know my rate law is going to look like this. Okay? Get this back so you can see. And I'm looking for M and N. So let's pick one and focus on it first. I always tend to do the first thing, so let's focus on finding M. So I just try to keep myself organized, that I'm looking at M. So I'm looking at how does changing A's concentration affect the rate? So if we want to change A, B has to stay constant. So what do I want to compare? One where A changes, or two experiments, where A changes but B stays the same. So that's going to be experiment 1 and experiment 3, A changes, B stays constant. So what we're going to do is kind of write a ratio, so to speak, of these rates, okay? So again, hear me out because this is a little bit lengthy. So I'm going to do a ratio of rate 3 over rate 1. Now, why I picked that is because I picked the bigger rate to be on the numerator of the fraction, so that when I divide this by this, I get a number bigger than 1. You can flip this upside down. It's just going to give you decimal numbers, and they're a little bit uglier to think about in your head. So my rule of thumb is always pick the bigger one, put it in the numerator. Okay, so now what we're going to do is essentially write a rate law for the data from the third reaction or experiment divided by a rate law for the first experiment, meaning this. So let's just focus on the rate law for the third experiment. So we're going to go back to here. So rate 3 is equal to K, all right, from experiment 3, so to speak, so you can label it if you want to, times the concentration of A from experiment 3 raised to the M, times the concentration of B from experiment 3 raised to the N. All I'm doing is using this general form and substituting it in here, understanding that it's going to be the data from experiment 3. And the same thing here, understanding that it's going to be the data from experiment 1. So this would be K1 concentration of A in experiment 1 raised to the M times concentration of B in experiment 1 raised to the N. And now I start to fill in some numbers. However, before we do that, I think it's important to look at a couple things. So this is the same reaction, A plus B yields C, it's just the concentrations have been changed. So if this is the same reaction and the temperature is the same, what's true about K3 and K1? Because it's the same reaction at the same temperature, K3 and K1 are the same thing. It's the rate constant for that reaction. So they're exactly the same thing, and so essentially they cancel out from this equation. And if you're noticing, the concentration of B in experiment 3 and the concentration of B in experiment 1 are equivalent. They're both 0.1. Well, 0.1 raised to the N divided by 0.1 raised to the N also cancel out, and they drop out from this expression. So all I'm left with is a ratio of the rates divided by a ratio of the concentrations of A. And now I fill in some data. So all we do is pull the data and fill it in. Rate 3, right there. Rate 1, right there. Okay, set it equal to the concentration of A in experiment 3, which is 0.2, raised to the M power. Okay, we still don't know M, that's what we're looking for. Divided by the concentration of A in the first experiment, raised to the M power. Okay, now let's simplify a couple things. This right here, well, these essentially drop out. 16 divided by 4, well, that's 4. And this, a rule of exponents, I don't know how many of you know this, is that rule of exponents says that you can do this and raise the whole thing to the M power if they're both to the M power in the numerator and the denominator. So now, essentially, again, this is lengthy. Essentially what we have now is 4 equals, can we simplify this? Oh, most definitely. 0.2 divided by 0.1, well, that's 2 raised to the M power. And what is the only thing that M can be? The answer, 2. So again, rather lengthy, but we have just solved now for this. And now we know that that's a 2. But we're not done because we have to do the same thing to solve for B. The order on B. But this is good because it'll give us practice again and another explanation. All right, so ready? So now this is for N. So N is on B, so I'm looking for how does the rate change when I change B, but I hold A steady. So best experiments would be 2 and 1, or 1 and 2, where B changes, A stays the same. So again, we're going to do the same thing. We're going to compare the rates of experiment 2 and 1. Now, if you look at this, the rates are the same. Remember I said you always put the big one in the numerator, so it doesn't matter. I'll just do rate 2 over rate 1. Again, you can fill all this out if you want, but if you want to make life easy for you, you know that your K's are going to drop out, right? And if you've picked 1 and 2 where A is being held constant, well then the A terms are going to drop out. So all that you're going to be left with is the concentration of B in experiment 2 raised to the n over the concentration of of B in experiment 1 raised to the n. Only because the K's canceled and the A's canceled, because the K was constant and the A was constant. If for some reason A was not constant, you cannot drop him out of the expression. We'll get to that later because that does happen. Now it's as simple as filling numbers in. So rate 2, 4.0 times 10 to the negative 5th over rate 1, 4.0 times 10 to the negative 5th equals B in experiment 2, that's 0.2 raised to the n, over B in experiment 1, 0.1 raised to the n. We simplify. This divided by this, well, that's 1. This divided by this, 2 to the n. The only thing that n can be, 2 raised to what power gives you 1? Well, it's not 1 because 2 to the first is 2. That doesn't work. So it's almost like a guessing check game. The only thing that works here is if n equals 0. Which means that this is now a 0. This is what we had before from our visual inspection. This whole term technically drops out of the whole term technically goes to 1 and drops out of the equation, which means my true rate law for this reaction is the rate equals K times the concentration of A squared. Now, I have answered only part A of this question, but part B and C are much simpler and will not take nearly as long. But we had to answer A to be able to answer B and C. So I'm gonna rewrite this. So the answer to A was rate equals K times A to the second. Remember, it really was B to the 0, but that term has dropped out. We don't need to include him. All right, so what does B say? B says the magnitude of the rate constant. Well, that's K, and magnitude means size. So what it wants me to do in this case is calculate the value of K. You might be asking how you do that when I have an unknown and an unknown. But see, in reality, we don't have an unknown. We have all this data up here. So for letter B, you pick any experiment in the data chart. Any of them. You can pick 1, 2, or 3, doesn't matter. And you fill in the rate, and you fill in the concentration of A, and you solve for K. Doesn't matter which 3 of these you pick, we will all get the same answer. So let's see. I'm going to do experiment 2. Actually, hold on. I forgot to bring my calculator in here. So I'm going to do whatever I have on my notes here. Which was experiment 1. So I lied. I'm going to use experiment 1. Okay. So I'm solving for K. So I want to get K by itself, which means I need to get rid of A squared. Actually, I need to get rid of A squared. So divide both sides by A squared. Gone, gone. And what we're working with right now is K equals the rate over the concentration of A squared. All I do is if I'm using experiment 1, I go to the chart and I plug in those numbers into this and solve for K. Simple as that. The rate is 4.0 times 10 to the negative 5th. Now this is where units come into play. I didn't put the units up here, but they're on your paper. Rate is measured in molarity per second. Divided by the concentration of A. In experiment 1, it was 0.1. Molarity, be careful though, because it is squared. Now, let's have a unit discussion. Molarity per second divided by molarity squared. That means 1 molarity is going to cancel with 1 molarity, and you end up with 1 over S times M, or conveniently, S to the negative 1, M to the negative 1. Remember from our last lecture that the units of the rate constant tell us something. They tell us the overall reaction order. Remember, if you take this and add them together, take the absolute value, so that would be 2. It should it should agree with the overall order of the reaction, and look at that, it does. So life is good. All I have to do now is my calculation in here. Now, when I cross this out, I shouldn't have done that because I can't forget that I have to square that guy. Oops, sorry. So it's just a unit that canceled. If you want, it's probably more helpful to write this like this. There. And then this cancels with that. Okay, so don't forget to square your concentration of A. And if you input that into your calculator correctly, you end up with a rate constant of 0.004. Technically the sig figs here, I should go one more, so put a 0 on there. Units of 1/seconds times molarity, or S to the negative 1, M to the negative 1. And there it is. Okay, that was part B. Oh, shoot, shouldn't erase that. Actually, it doesn't matter. So here, I'll just summarize my answers. So A was rate equals K, concentration of A squared. B, it was K equals 0.0040 M to negative 1 S to the negative 1. And now C asked me to find the rate when A is equal to 0.05 molar and B is equal to 0.1 molar. That's what the question says. So if I'm finding rate, I'm looking for this guy. So to find rate, I need K. Just found it. Look at that. So I'm going to plug this in for K, and I'm going to use the concentration that they gave me in the question in part C for A. Now notice they gave me a concentration of B, but since B is not in the rate law, it doesn't affect the rate, so I don't need to worry about that. So all I do is plug everything in. So K is 0.004 molarity negative 1 seconds negative 1 times the concentration of A that they gave me in the problem, which was 0.050 molar squared. All I have to do, crunch this in the calculator correctly, and I will end up with the rate. So you go ahead and do that. Don't forget to square this. Remember, it's coming from your order. 2 sig figs. And I end up with 1.0 times 10 to the negative 5th. If you didn't get that, go back and double check. You've made a calculation error somewhere. And let's talk about our units for a minute. If this is easier for you to write like this, then that's fine. So it's this times molarity squared. And look what happens. Gone, gone. Units of molarity per second, which is in fact the correct unit for a rate. And there is the answer to letter C. So that's a loaded problem. It's very lengthy, those 3 parts, but that's how you solve it. And we're going to be solving many more like that. So if you turn your paper over, there's a second example, very similar to this, exactly the same setup. I want you to work on that, and there will be an additional, a second video with the full explanation of how to solve example 2.